K2 brings us to rotational dynamics. We have already looked at in the previous section rotational kinematics. So the first question we're going to ask is, what is analogous to force that'll get something to rotate? So if we have a circular, say, disc of some sort here, and we're looking at a distance, say r away, we apply a force. This force will get this to rotate. If you apply the force at the center, it's not going to make it rotate, just trying to pull it like off where it's fastened. So here, if we have the F and the R, what we're going to do is make a definition and say that the torque, tau, the Greek letter tau, is R times F. Now there's no physics yet. This is a definition, which makes sense because the force being applied at a greater distance from the center will have a greater effect on getting this to rotate. Now we may ask the question, suppose that the force is at some angle like this. And we'll call this angle here phi, and this angle in here theta. I like to put 2 notches on one angle, like in high school, and indicate that the angle's different, but not everyone does that. As long as you have them labeled like this, you're in good shape. Notice that here, in this case, the component of the force to the right is trying to just pull a disc off its location. What's going to get it to rotate is the component that's perpendicular, like up there. So if we take, for the torque now, R times F, we want the cosine of phi. Now we can also write this as the sine of theta. So the sine of theta here times F is this upward component. It's the same. These angles are complementary. Their sum equals 90 degrees. Now what we can do is assign a direction for the torque. If you take your right hand and curve it along the counterclockwise direction, in this case, the thumb points up, straight up, and the thumb then gives the direction. This is called the right hand rule, and in our text we have this picture to remind you of what I just did. So let's call that direction up out of the page by a unit vector n hat. Then we can assign a vector to the torque, R times F, sine of theta with the n hat. And then we can look at these two parameters, R and F, and write them as vectors. Here is the R vector. Could put a little vector sign there. And then F goes here, and I like the angle theta. People like that because it's the angle that's made between the two vectors. So if we look at F and we look at the R vector like this, then we can arrive at this vector from these two vectors by the cross product. So the cross product, you can think of the cross product as being defined to mean what we just have there, R cross F. This means you take the magnitude of the R vector, R, the magnitude of the force vector, F, and the sine of the angle between them, sine theta, and then apply the right-hand rule like this. Now, this is a general formula for the cross product, and in math books, they'll write something like this: A cross B is equal to A times B times the sine of the angle, and then you use the right-hand rule to get the direction. That's called the vector cross product, or simply the cross product. And there's a neat way to get that direction with your right hand. What you can do is you can put we show the picture here. What we can do is put one finger here, okay, this like forefinger in the direction of A, then the index finger along B, and then you bring the A to the B, A cross B, and the thumb is pointing in the direction. Now, when I first learned this, I learned it by thinking of a screwdriver where you're tightening a screw, a right-handed screw. Most screws in the United States are right-handed, so you would tighten by going, you would tighten, for example, if you had a screw here, you were going to tighten it, you would go this way. And there's some like way to remember this. I heard something like righty-tighty and lefty-loosey or something. To loosen it, you go to the left counterclockwise and clockwise if you want to tighten it. So in that case, I'm going to show you that way of looking at it. It's the way I do it. If you take the screwdriver and want to turn A into B, to tighten it from underneath, you would be going up. Now, if you like this way, you use the right hand. A lot of students just like that way. But I learned it this way, so this is the way I use. If I want to turn the A vector into the B vector, I have to go underneath. See, if I were at the top, I would be turning down. I would be turning the red one into the blue one. I don't want that. I want to go the blue one into the red one. So whatever works for you is fine. So then here, we can note something cool, is that if you have a vector A and you want to, say, cross it with itself, you would have A times the sine of 0, since 0 degrees. And the sine of 0 is 0, and you would have some kind of like unit vector there, and so therefore this is 0. So a vector with itself, if you cross with itself, is 0. And if you were to reverse this and go B cross A, well, in that case, you would then want to have the B go into A, so you would have the screwdriver at the top to turn it, so that you would get the red one to go into the blue one, and then look, you're going in the minus n direction. You're going down. So when you flip this, you get a minus sign. So A cross B, see, is negative B cross A, and vice versa. So I would like to call this subsection that we're doing here, I would like to call that torque, where we define the torque, which is analogous to the force. And then for section 2, I would like to call this angular momentum, to find what's analogous to momentum. Now, here, we're going to start to get into physics and dynamics, because the force, Newton's second law, is dP dt, it's derivative. And if we look at what the torque is here by our definition, we're going to calculate what the torque is using the law of physics here to bring the physics into the definition. So R cross F is equal to R cross dP dt by simply doing R cross on both sides of the equation. And this is equal to the torque. So now we have a physics equation. With our definition of torque, we are now relating it by Newton's second law to some kind of change in the momentum. So if we look at this equation, this is a very, very interesting trick that we're going to do. That if we look at say dr dt cross p, I'm going to show you that this is 0, so I can pull the ddt out in front and have a product rule. But before I do that, let me just show you why this is 0. This derivative of the r is going to be the velocity. And since the momentum is mass times velocity, I get m times v cross v, but we said, see up here, that if you have the same vector and cross it with itself, you get 0. So now you can see the trick. I can write the torque equation as d dt with the r cross p on the outside. And when we use the calculus derivative rule for products, you would take the derivative of the first cross p, which is 0, and then you would take r cross the derivative of the second, which is this term here. So by simply adding 0 in this form, we can then get this nice relationship. And then this is analogous to momentum, because remember, F is dP dt, and this is saying that the torque is equal to some change in some other vector quantity, where this L is r cross p, and that is called the angular momentum by analogous equation. Very, very nice. Now for section 3, what I would like to do is get the equivalent analogous quantity for the inertia, and I'll call that rotational inertia. So what is the resistance like to have something rotate? And the guide here, say we just draw a little picture. So here's an axis, and we have something here. Say this is very, very light, and you have a mass on the end, and there's some inertia, that reluctance for the rotation to occur. You have to then do some work. You have to like push on it to get it to do that. And we're going to do this with the idea of kinetic energy. The kinetic energy is 1/2 mv squared. But we know that the v of this mass going in a circle is related by omega r from our earlier section. So this is 1/2 m omega r squared, and this is equal to 1/2 m, I'll put the r squared first, and then the omega squared. Now this is analogous here to a inertia term times a velocity term, and here you have the angular velocity. So it's this piece here, which is the rotational inertia, which we call the moment of inertia. So the moment of inertia for a mass, point mass, is mr squared. Now, if you have lots of masses that are doing the same rotation, then what you would do is you would have a sum. You would be adding these up. So if you had lots of masses, m sub I, at distance r sub I, you would then have a summation of the mi ri squared, like this, and this would be the formula for the moment of inertia in general. Now notice that the kinetic energy, here's 1/2 mv squared. The kinetic energy for rotation would be 1/2. The analogous thing to the m is the moment of inertia, and the analogous thing to the velocity is the omega. So you would have this nice relationship here with the moment of inertia being given by that general formula. So you can see that if you had, say, a dumbbell like this, and you had oriented the dumbbell like this, that this one would have more inertia, more moment of inertia, since the masses are farther away from the axis. So it's harder to get this thing to spin around compared to this one where the masses hug the axis. So you have a neat little picture in the text showing that. Notice though that when you have the rotation of, say, a wheel that's traveling down the road, then you would have 1/2 mv squared plus 1/2 I omega squared, because a wheel is moving, that's traveling down the road, is moving along the linear direction and also rotating. So a neat little diagram to help us understand this is to have the pure translation and the pure rotation. And when we combine these together, we get the rolling ball. Notice that the velocity in the middle is v, and the velocity at the top, v plus v, is 2v, and the velocity of the point down at the bottom is 0. Actually, that velocity is 0. It's cool. So you have this velocity v, and remember that v is omega r, where r is the radius of the wheel. So therefore, you can write this kinetic energy as 1/2 mv squared plus 1/2 I, and omega here is equal to v over r. So this would be v over r squared. So that's the total kinetic energy for the case of rolling. Nice.